Welcome to Daily Papers, the podcast where we break down the latest and greatest in the world of research.
Today we have a paper that sounds almost too good to be true. The title is Smarter and Cheaper at Once, which is basically the holy grail for any technology.
It really is. The standard approach in AI for years has been pretty straightforward. If you want a smarter model, you build a bigger model. If you want it to run faster, you buy more expensive hardware. It's a cycle of more data, more power, more cost.
And there's a hidden cost people don't often think about. Every time you chat with an AI, it has to reread and reprocess the entire conversation from the beginning. It has this temporary scratch pad for its thoughts, but once you're done, that scratch pad is wiped clean. It's incredibly forgetful by design.
Exactly. So this paper asks a really simple question. What if we didn't wipe the scratch pad? What if when a model does something really clever, we could save that thought process and just reuse it later?
And that's the core idea. They've developed a way to save this scratch pad, which in technical terms is called the KV state or KV cache. They save it to a hard disk, and then later they can graft it back into the AI's short-term memory.
Now, lots of systems do something like this, but the secret sauce here is one critical term, Byte-Exact. What they save and restore is a perfect, bit-for-bit, identical copy of the AI's mental state.
It's not an approximation or a fuzzy memory. It is, provably, the exact same state the model would be in if it had done all the work from scratch. This means there is zero loss in quality. It's like the difference between someone telling you the gist of a book versus you having read the book yourself.
This Byte-Exact guarantee is the foundation for what they call the verified knowledge flywheel. The process is simple. First, you give the AI a hard problem. It might take a lot of effort, but eventually it finds a solution.
Then, step 2, you verify that the solution is actually correct using an external tool. This is the verified part. You don't want to save a wrong answer.
And once it's verified, you save that entire successful thought process, the KV cache, as a permanent file. Now the flywheel is ready. The next time the same or even a similar problem comes along, the system just finds the right file and grafts it into the model.
The AI essentially gets to skip all the hard work and start from a position of already understanding the problem. So the big question is, does it actually work? Does this make the model smarter?
The results are pretty staggering. They took a 12 billion parameter model called Gemma and tested it on a tough math competition benchmark. On its own, the model scored a respectable 80%.
But after they used this flywheel method to teach it how to solve the problems it was struggling with, its score jumped to 93.3%.
To put that in perspective, the bigger, supposedly more powerful 31 billion parameter version of that same model scores 89%. So this technique made the smaller, dumber model outperform its massive older sibling. It's like a high school student suddenly acing a PhD exam because they were given the professor's notes.
Okay, so that's the smarter part. What about the cheaper part?
This is where it gets truly wild. They looked at 8 specific problems that the base model consistently failed to solve. To even try, the model spent over 400,000 tokens. A token is basically a piece of a word, and it's how you measure and pay for AI computation.
So 400,000 tokens to get 0 correct answers. That's a lot of wasted effort.
Right, but with the flywheel system, once the solutions were saved, the model could solve all 8 of those impossible problems using a grand total of 61 tokens.
Wait, 61 tokens for all 8 problems? Not per problem.
For all 8. That's about 7 or 8 each. It's a 6,574-fold reduction in the amount of computation needed. The paper estimates this uses somewhere between 3,000 and 8,700 times less energy. It's the definition of work smarter, not harder.
That is an insane efficiency gain. And they don't just stop there. They also use this technique to expand the model's memory, or what's called its context window.
Yeah, usually a model can only really remember a certain amount of text at one time, say 32,000 tokens. If you want more, you need a bigger GPU, which costs a fortune. But because this system stores knowledge on the cheap hard drive, they expanded the model's usable context by 87 times to almost 3 million tokens, with 0 extra cost for the expensive accelerator memory.
So the AI can effectively read and reference a massive library of information without needing a supercomputer to hold it all in its head at once.
Exactly. Now, the authors are also very honest about the limitations. The big one is that this byte-exact trick only works if you graft the memory back into the exact same position it came from. You can't just drop it in anywhere. It's like a puzzle piece that only has one correct spot.
Which is a totally fair limitation. It doesn't break the idea, it just defines the rules of how to use it. And it only really helps when the model is struggling. If the AI can already solve a problem easily, there's nothing to gain.
But that's the point. It targets the most expensive and difficult problems, the ones that consume the most resources, and makes them trivial on the second try.
So the final takeaway here is pretty profound. Instead of being on this endless treadmill of building bigger and bigger AI models, this suggests a different path. We can take smaller, more efficient models and make them vastly more capable and cheaper to run by giving them a perfect, verifiable memory.
It's an economic argument as much as a technical one. The philosophy is solve once, never pay again. And based on these results, it's a very, very compelling one.